Hi everyone, this is the case study video for the subject Digital Electronics and Linear Integrated Circuits. This case study subject is nothing but we are going to discuss about a design of a decade counter, which is discussed by second year degree students of SNS College of Technology, Mr. Sriram, Mr. Kiran, Mr. Sabarish and Mr. Sadish. Now let me see the discussion. First, let me ask what is a decade counter and how it is explained with the help of a state diagram. The explanation is started by Mr. Sriram of second year.
A state diagram. Similar sequential often decade counts means 10 count. 10 count where starts from 0 to 9. First, step 1 we are going to see about state diagram. What is state diagram? It represents a graphical representations of a state with represent the next with the arrow mark. First we are going to see what 2 to the power 4 where which is a 4 literals starting from 00002 again it goes on and it starts from 9 10001 and repeats to 0 and cycle repeats. This is about the state diagram.
Now let me discuss about this. This is a state diagram of a decade counter. Since it is a 4 bits, it starts from 0000 at the present state. The encrypted value is the present state and the arrow mark represents the next state. It is clearly explained by Kiran. Now let me see the next step, which is nothing but the excitation table by Mr. Kiran of second year.
In the step 2, we are explaining about the excitation table. The excitation table we have split it into 3 types: present state, next state, and output. We have 4 letters. There are QD, QC, QB, QA. And the next state we have QA, QD1, QC1, QB1, and QA1. We should return for 15 letters up to 0 to 15. First we should take it as a simple. First we should take it 3 and explain it. First we take as a 4 letters of 000 for zero's value, and the next state we have 1 value. We should present it as a 001. Then it will be same as the next present state of 0001, and we should tell about the same thing for all the things up to 0 to 50. In an XOR gate, the output value will be usable with the truth table of XOR gate. In XOR gate, everyone knows 0 is 0 and 0 1 is 1 and 1 0 is 1 and 1 1 is 0. So we should apply this in the present state and next state. First we should take it as a QD and QD plus 1. We should see the first values are 0 0. 0 0 in the truth table of XOR 0 0 is 0. So we should return as a 0. And the second state 0 0. The same will be written for the first 3 components. In QC, the same 0 0 0 0. In QB and QB plus 1, 0. 0, the next value 0 1. In XOR gate, 0 1 is 1. So we take it as a 1. And 1 1. XOR gate, 1 1 is 0. QA 0, QA plus 1, 1. 0 1, 1. 1 0. 0 1, 0 1 1. In the similar way, we should continue it for the 15 letters.
Now for this excitation table, we have to solve the minimized expression for all the outputs. The output is TA, TB, TC and TD. There are 4 outputs. For all the 4 outputs, we have to solve with the help of K-map. Now let me invite Mr. Sabarish for solving this K-map. Sabarish.
When we see about output table, K-map without using K-map, TB. The decimal values 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We see about TB. TB equal to 1 value 1, and 3 values 1. And the seventh also. These do not care. Using came up with balance area 0. Put 0. The TB came up is 1 quarter. This value is common value. TB value is QA, common values Q bar D. This product TB came.
Okay, now for this is the KMAP which is solved for this TB. This solved for this TB. Now we have to solve for all the remaining outputs. You mean TA. We have to draw a KMAP for finding what is the expression for TA. Similarly for TC and TD. If all the KMAPs are done and the output expression may be like this: QA and Q bar D. And this is for TB, and similarly for TA, TC and TD may come.
And similarly solve to the TA, TT, TD. And the value TB value is QA, Q dash D, TA value is 1, TC value is QA, QB, TD value is QA, QB, QD plus QA, QB, QC. It is
okay. Now after this expressions, the circuit is derived. The circuit is derived by Mr. Sriram. Yes, and is explained by Sriram.
Where the input TA, TB, we have for A and B and C and D, where TA, TB, TC are the input and QA, QB, QC and QD are the outputs. We were drawn the 4 similar square diagram, and one input is passed to the TA and other clock pulses pass through the all others, and in here TD from QA and QD. QA and QD were joined with an AND gate by similar. All of them are connected by AND gate, and lastly and QD where QA and QD and QA BC are connected with an XOR gate, and the logic circuit is derived.
Now this is the output. This is the A flip flop, which is nothing but LSB, least significant bit, and D flip flop is MSB, most significant bit. And these are all the outputs. The output is, this is A, you mean QA, QB, QC and QD, right? This is your output. This is the output. Now for practically implementing, we have to purchase T flip-flop. We have to purchase 4 T flip-flops, and this flip-flop ICs has to be installed in the breadboard. And if we connect these wires and the supply is given for all the flip-flops, then a counter, you mean as per the students explained, a decade counter will be delivered as an output in QA, QB, QC and QD. And thank you for this designing of a decade counter, synchronous sequential decade counter. And this is explained by our 4 students, second year 4 students. And thank you for explaining this. Thank you.